All right, so today we will get started on a new topic. Much of what I'll be saying today would be a straightforward extension of whatever we covered in the second order differential equations. And in particular, we are going to look at higher order ODEs. Okay. So the general form of these, so it could have d cubed x over dx cubed, or fourth derivatives or seventh derivatives, or whatever it is, in general nth derivatives, excuse me. And the general form of such equations is f of y to the n minus 1 equals 0. Okay, so this is a general nth derivative higher order linear equation. So I'm also writing it in the homogeneous form. Okay, so basically I don't have anything on the right? I don't have any function r of x on the right so far. So when do I say that such an equation is linear? I claim that such an equation is linear if I can write it in the form dn dx plus some dn minus 1y dx n minus 1 plus all the way till p1 dy dx maybe I should call this pn, doesn't matter what I call this, equals 0. Okay, so this is a linear homogeneous nth order ordinary differential equation. Okay, so I should mention at the beginning that in general, higher order differential equations don't play as prominent a part in physics and mathematics, in physics and engineering as second order differential equations do, but there are certainly cases where they pop up. And in many of these cases, you can understand the solutions by a simple extension of whatever you will learn in the second order case. So that will be the focus of today and the next lecture. So basically, to try and extract as much as possible, at least from the homogeneous higher order ODEs, based on your knowledge of second order differential equations. Okay, so wherever the extension is straightforward, I will actually simply just mention this. Okay. All right, so let us get started on this subject. So the first thing to do is, how do I write down the solution for the homogeneous equation, and what does the solution look like? Well, if I put n equals 2, you know everything about solving, at least with constant coefficients, you know everything about solving such equations, right? So you know that there is two linearly independent solutions, pi1 and pi2, and then any general solution can be written as a linear combination of these two solutions, which means that there are no singular solutions for second order differential equations. And they've also learned a little bit about the existence and uniqueness of the initial value problems and things like that. And all of these statements that you have learned have straightforward extensions in this case also. Okay, so the first thing is, if I want to solve the homogeneous equation, superposition holds. Superposition holds. Okay. So in other words, the solution of this homogeneous equation can be written as C1y1 plus C2y2 plus all the way till Cn yn. Okay, where y1, y2, yn are n linearly independent solutions. Okay, and these form a basis. Okay, so in the second order differential equation case, your goal was to find the two linearly independent the solutions, and in this case it's slightly more complex. You'll have to find n of them. So if you're tasked with a third order differential equation, you have to find 3 linearly independent solutions. So there is two questions that emerge. How do you find them? And how do you know that they're linearly independent? Okay. So let's answer the second question first, because it's slightly simpler to answer. So what do I mean by linearly independent solutions if I have more than two solutions? Linear independence. So remember that when we started with the notion of linear independence, in the case of second order, we said that suppose if I write an equation of the form k1y1 plus k2y2 equal to 0, right? Then y1 and y2 are linearly independent if the only solutions of this equation are k1 equals k2 equals 0. The only solution is the trivial solution. If this equation holds true for non-zero k1 or k2, then I can write either y1 or y2 in terms of the other, and they won't be linearly independent anymore. Okay. And then we sort of went ahead and said that we can write this in a slightly more robust way that also generalizes by using the definition of Wronskian. So what did we do in the case of Wronskian? We simply said that, look, I have this equation, right? So since I'm dealing with second order linear differential equations, I can also differentiate these guys because the second derivative exists and obviously the first derivative also exists. So now if these have a trivial solution, then it means that the determinant of the coefficients of k1 and k2, which I can write as y1, y2, y1 prime, y2 prime, the Wronskian has to be equal to 0. Okay. This means they are linearly dependent. Okay. So I can extend these notions in the case of nth order linear differential equation also. Okay. So in general, using just this check might be a little difficult, but using the Wronskian is more fail-proof. So what do I mean? In the case of higher order differential equations, linear independence means that, again, if I form an equation of this form, k1y1 plus k2y2 plus knyn equals 0, then if I can write any one of these in terms of the other, if the only solutions are all the k's are equal to 0, then I'm dealing with linearly independent solutions. But if I'm able to form a solution with a non-zero k, then I can write one of these guys in terms of the other. So which means that at least one of these solutions is linearly dependent on the other, which means I have to do a little bit more work to figure out one more linearly independent solution. Okay. So again, instead of formulating it this way, which is perfectly okay, but practically not very useful in cases where you have, like, fifth derivative equations and things like that, it's much better to use the notion of Wronskian. So again, since these are differentiable n times, because these are solutions of an nth order differential equation, I can differentiate and form equations of this sort. Yn prime equal to 0, and I can keep going. K1, y1 to the n minus 1th derivative equals 0. Okay, so I should also mention that I'm using a shorthand notation. So if I write yn, it means dny over dx to the n. Okay. Again, if all these solutions are linearly dependent, then the matrix of these guys has to be equal to 0. In other words, I can define a Wronskian in this case also. Y1, y1 prime, y2 prime. Oops, excuse me. Y1 prime, y1 double prime, all the way till. Okay. So arrange the columns this way. And you keep going. This is obviously an n by n matrix. And if the Wronskian is non-zero, then you can conclude that you have found a set of linearly independent solutions. And if this Wronskian is equal to 0, then you're dealing with linearly dependent solutions. Exactly the same way as you looked at the second order differential equation case. Okay. So far so good. Any questions? So suppose if you want to look at an example, let us say that you solved some third order differential equation and you got your solutions as y1 equals e to the x, y2 equals e to the 2x, and y3 equals e to the 3x. Okay. So suppose if there is some differential equation that gives you these three solutions, we will get to the solving part a little later. So how do I show that these are linearly independent? Well, I know that if you only have e to the x and e to the 2x, I hope that by now you know that those are indeed linearly independent. But now I'm extending this slightly by including a third solution. So I will write down a Wronskian. Y1 is e to the x, y1 prime is e to the x, and y1 double prime is also e to the x. Okay, that's simple enough. Y2 is e to the 2x, y2 prime is 2e to the 2x, and this is 4e to the 2x. This obviously is e to the 3x, 3e to the 3x, and 9e to the 3x. Okay. And then you can go ahead and solve this determinant, and this determinant is obviously not equal to 0, as you can quickly verify. The easiest way to do this is to pull out a factor of e to the x from the first column, e to the 2x from the second column, and e to the 3x from the third column. So you have an overall factor of 6x. So you have 1, 1, 1, 1, 2, 4, 1, 3, 9, and you can check that this obviously is non-zero. Okay, so this tells you that these three are linearly independent. Okay, so this implies that e to the x, e to the 2x, e to the 3x are linearly independent. Okay, any questions or any comments about this? So the check is actually straightforward. You simply extend the idea of Wronskian. But depending on what kind of equation you deal with, suppose if you are dealing with a fourth order differential equation, you have to deal with a 4x4 matrix. And if you're dealing with a third order differential equation, you have to deal with a 3x3 determinant and so on and so forth. But it can be done. Okay. So I'll say a few words about how to set up the initial value problem in the case of a higher order differential equation and under what conditions solutions exist. So initial value problem, existence and uniqueness. Just like we have been thinking about these for first order and second order, we can also formulate the exact same question for higher order. So how do I formulate the question? So the way I formulate an initial value problem is as follows. I'll first supply the differential equation to you. The differential equation is dny dx to the n plus pn minus 1 dn minus 1 dx n minus 1 plus p1 dy dx plus p0y equals 0. So I'm only dealing with homogeneous nth order differential equations for now. Okay, I'm not adding any inhomogeneous term on the right hand side. So initial value problem means that I have to supply the differential equation and the initial conditions. How many initial conditions should I supply in this case? Well, I'll have to supply n initial conditions, right? So if I have a first order differential equation, I need to supply only one constant of integration. If I have a second order differential equation, I have to supply two, right? Position and velocity, for example. If I have an nth order differential equation, I'll have to supply n initial conditions in order that you might be able to get a particular solution completely unambiguously. Excuse me. So n initial conditions. And these conditions can be written as y at some point, x0 is k0, y prime at some point x0 is k1, so on and so forth till y n minus 1 at x0 is some k n minus 1. Okay, it is not necessary that I supply all the initial conditions at the exact same point x0. In this case, I've just written it like that for simplicity. But for example, I can supply y at x is equal to 2 and y prime at x is equal to 5 and so on and so forth, and that's totally fine. I just need n conditions on the n derivatives, n minus 1 derivatives and y. Okay. So exactly like you had for the second order differential equations, if all these functions that you see, which in general are functions of x, right? So these are functions of x. If all these coefficients are continuous functions of x in some open interval I, and if the initial point that you specify, which is x0 in this case, is in this open interval, then this initial value problem has a unique solution. Okay, so I'll write this statement down. If the coefficients, excuse me, P0, P1 are continuous on some open interval I, and x0 is in I, then, so I'll call this equation 1 and equation 2, then the IVP 1, 2 has a unique solution on I. So this is again a straightforward extension of what we studied for the second order differential equation case. Okay, so there is nothing more to be said here. So of course, this presupposes that you know how to write down the general solution. So let's say a few words about the general solution also. Okay, so what do I mean by a general solution? So general solution, if the coefficients P0, P1, etc., all the way till Pn minus 1 are continuous on some open interval, then the ODE 1, okay, has a general solution. Okay, so again, please don't confuse these two statements. The conditions are the same, except that the coefficients being continuous guarantees the existence of a general solution for equation 1. And then if you plug in the initial conditions, this condition also ensures that your IVP also has a unique solution. Okay, so there is no, for example, multiple solutions that will give rise to the same initial conditions. Okay, so once you specify your general solutions, then basically you appeal to the initial conditions to fix the constants. And once you fix the constants, you can write down the solution in a unique fashion with all the constants determined. And the first statement is that this particular solution is indeed unique as long as the coefficients P of x are continuous. The second statement simply says that, well, forget about the initial conditions, just look at the differential equation. This differential equation always has a general solution on some open interval as long as all these functions P0s, P1s, etc. are well behaved in this open interval. Okay. So again, what do I mean by an open general solution? I mean that it includes all possible solutions. In other words, if someone comes to me and says that they have found a solution y of x for this ODE1, then any solution y of x of 1 can be written as a linear combination of the basis solutions. In other words, if somebody says they have a solution y of x, I'll claim that this y of x is nothing but some linear combination of the y's that I have found out. Okay. So what this statement again means is that the general solution is the y1, y2, and so on, contains all possible solutions. Any solution that you come up with can be written as a linear combination of the basis solutions. Turning this around, we also claim that there can be no solution that cannot be written as a linear combination of the basis solutions. Okay, so there cannot be any solution that is not expressible in this form. Okay, that is, there are no singular solutions. So structurally, first order differential equations are therefore different from second order and higher order differential equations, because as we found out, first order differential equations do permit singular solutions, but higher order differential equations do not. Okay, so again, these are all extensions of what you studied in the case of second order differential equations. Okay, so this sets up the basis of higher order differential equations, and what remains is basically, once we have convinced ourselves that a given differential equation has a solution and that the initial value problem posed is actually meaningful, then our goal is to basically find the solutions. Okay, so I'll say a few words about finding solutions now, and then we will take this up in the next lecture. Okay, so again, we will concentrate on the constant coefficients problem. Constant coefficients. Okay, so we will take up the case of general coefficients, varying coefficients like p of x and p1 of x, etc., in the next lecture when we talk about series solutions of differential equations. For now, we will stick with constant coefficients and try to figure out some ways of getting the solutions. So this is best done using a couple of examples. So I'll first work out an example, and then I will generalize this case. Of course, this doesn't encapsulate all the possibilities. We will talk about a couple more cases in the next lecture. The case that I will talk about now is a fourth order differential equation. Of course, this is a very simple equation, but I simply want to point out to you how the solutions occur. Okay, so the way you would solve these constant coefficients example, even in the case of higher order differential equations, is exactly how you progress to the second order case. In the second order case, basically we tried a solution of the form e to the lambda x, right? And then we plugged this in the differential equation and we got a quadratic equation for lambda, which gave us two roots. We will do the exact same case here, except that the structure is slightly more complicated, which means we will get more roots. For example, if you have an nth order differential equation, if you plug this in, you will get an nth order equation, right? It won't be just quadratic. If you have, for example, a third order differential equation, you'll get a cubic equation, and you have to solve the cubic equation and you have to get the roots, and then you have to investigate whether these roots are real or imaginary, and then accordingly your solutions will have different forms. Okay, so this is a rather simple example, so let us actually do this. So again, in this case, y prime would be lambda e to the lambda x and so on and so forth, right? So yn would be lambda to the n e to the lambda x, because it's a simple enough ansatz. So if I plug this in this differential equation, what do I get? So 4 derivatives of y will pull down 4 powers of lambda. So I'll get lambda to the 4th. Second order will pull down 2 powers of lambda. So 2 lambda square plus 1 times y equals 0, right? Of course, we don't want y to be equal to 0. We are looking at non-trivial solutions, which means that our characteristic equation in this case is lambda to the 4th plus 2 lambda square plus 1 equals 0. Okay. So this is, of course, a 4th order equation. But in this case, of course, since a linear term in lambda is absent and a cubic term in lambda is also absent, I can turn this effectively into a quadratic equation by claiming that lambda square is some other parameter mu. Okay, so this only works for this particular trivial example. Then this becomes a second order, sorry, this becomes a quadratic equation in mu. So I'll write this as mu square plus 2 mu plus 1 equals 0, which of course is mu plus 1 whole square equals 0, which means mu is plus minus 1. Okay. What happens if mu is plus minus 1? Well, what are the possible values of lambda? So lambda square is plus minus 1. Okay. Which means lambda can take the value. If lambda square is 1, of course, lambda is plus or minus 1. So plus minus 1. And if lambda...
So it's only minus 1, right?
Sorry, what?
Mu is only minus 1.
Yes.
Mu is only minus 1. Thank you. Yes. Mu is minus 1. So lambda square is minus 1. So what are the possible values of lambda in this case?
So plus or minus iota.
Lambda is plus minus I, right? But remember that this is a 4th order differential equation. So I should be able to get 4 linearly independent solutions, right? So this tells me that my possible solutions are e to the ix, e to the minus ix, right? So how about the other two? Can someone take a guess what they will possibly look like? We'll talk about this a little more in the next lecture. But based on your knowledge of second order differential equations, can you guess what the answer is? Guessing is an important skill.
Sir,
C bar I.
x into e to the ix.
That is one. Then the other is?
X e bar minus ix.
Very nice. So in this case, you can guess or figure out, we'll actually figure it out, but you can actually guess that the 4 solutions in this case would be e to the ix, x e to the ix, e to the minus x, x e to the minus x. Okay, so you could go ahead and plug this in the differential equation and show that each one of these actually solves the differential equation. And as a homework, show that W is non-zero in this case. Okay, the Wronskian is non-zero. So in general, if you have a constant coefficients problem, so n, if I write on an nth order differential equation, yn plus, I'll write this a instead of p because these are all constant coefficients, constant numbers, yn minus 1, a1 y prime plus a0y. So homogeneous equation is 0, right? Then I can write, if I plug in the ansatz e to the lambda x, this is going to give me a characteristic equation that looks like lambda to the n plus a n minus 1 lambda to the n minus 1 plus a1 lambda plus a0 equals 0. Okay. And then, of course, this is going to give me, if I am good enough to solve this, it's going to give me n roots. And then I'll have to understand what these roots are, whether they are real or imaginary or whatever it is. Okay. So Let us look at the first case today, and then we will look at the other cases in the next lecture. So the first case that we will look today are distinct real roots. Okay. So as an example, consider the equation y triple prime minus, again, I'm using many different notations, so I will stick with one. Sorry about that. So I'll write this as y3, which means d cubed y over d. Is the handwriting legible? I should make this slightly bigger. y3 minus 2y2 minus y1 plus 2y equals 0. Okay. So again, written in the entire gory form, this means d cubed y over dx cubed minus 2 d squared y over dx squared minus dy dx plus 2y equals 0. Okay. So plug in the ansatz, lambda, sorry, y is some e to the lambda x. Okay, for constant coefficients, this is always the most straightforward methodology. So this gives me an equation, lambda cubed minus 2 lambda squared minus lambda plus 2 equals 0. Who's good at solving cubic equations?
Sir, lambda is 1, minus 1 and 2.
Very good. You guys are very good at solving cubic equations. So this is lambda is plus minus 1 and 2. Okay, so I can write down the solution in this case, and these are distinct and real because I'm not getting any double roots and so on and so forth. Unlike, for example, in the case that we investigated before, which was neither real nor distinct. In this case, I can write the solutions as C1 e to the lambda x, sorry, C1 e to the x corresponding to lambda equal to plus 1 plus C2 e to the minus x corresponding to minus 1 plus C3 e to the 2x. So notice that all the lambdas are distinct. And in this case, the Wronskian also has a very nice form. I'll say a couple of words about this and stop. So if you form the Wronskian, assuming that your solutions are of the form e to the lambda 1x, e to the lambda 2x, where all the lambdas are distinct, right? Then if you form the Wronskian, how does your Wronskian look like? So you would have y1, right? And then you would have y1 prime, which brings out one factor of lambda. And then y1 double prime, which brings out two factors of lambda 1. And then yn minus 1, which brings down n minus 1 factors of lambda 1. And this keeps going, right? Lambda 2 square, and then finally e to the lambda nx n minus 1 e to the lambda nx. This would be your Wronskian. Okay. And you can show by general arguments that this is indeed non-zero. So again, the way to do this is to pull out an e to the lambda 1x from the first column, e to the lambda 2x from the second column, and so on and so forth as determinant. So you would have an e to the lambda 1 plus lambda 2 x outside. And then this becomes 1 lambda 1 square, 1 lambda 2 square. Okay. Have you guys had a linear algebra course?
Yes.
Yes, sir.
Have you seen determinants of this form?
Sir, this will be of the form lambda 1 minus lambda 2, lambda 2 minus lambda 3, and means all the possible duos of lambda I will be there as a It will be as a product of differences.
Very good. So it will be a product of differences. So this will be, it can be decomposed into a product of differences of lambdas. Okay, not double counting lambdas. Okay, so there is the exact form itself is not important, but the two things that are important here, it's a product of differences. Well, the difference of any of these two lambdas is not zero because we are dealing with distinct lambdas. Okay, since the difference of any of these is not zero, the product of these cannot be zero also. Okay, now remember that lambda 1 can itself be zero. That is certainly allowed. But lambda 1 doesn't come by itself in this determinant because it is always of the form lambda 1 minus lambda 2 or lambda 1 minus lambda 4 and whatever it is. Okay. Now, if two of these are zero, of course, then we have a problem, but that is not the case we're investigating, right? We are investigating the case where all these roots are distinct. So this Wronskian can never be equal to zero because it can be decomposed as a product of the differences of the lambdas. And of course, the exponential on the outside the determinant is, of course, never equal to zero. So which means that if you have distinct real roots, then the linearly independent solutions are e to the lambda 1x, e to the lambda 2x, all the way till e to the lambda nx. This is probably the simplest case where you have a differential equation that can be written down as a linear combination of whose solution can be written down as a linear combination of the exponentials, where all the lambdas are real. Okay. Of course, it doesn't always have to be this way, and we have to look at cases where you have repeating roots, and in that case, of course, the e to the lambda x's won't be the solutions. And suppose if I have, for example, I will just say this in words, and we will talk more about this in the next lecture. Suppose if I have lambda 1 repeating 3 times and lambda 5 repeating 2 times, right? So let us say you have the roots are, for example, 1, 1, 1, 2, 3, 3, 4, and 5, then corresponding to the root 1 and the root 3, which are repeating, your solutions will have to be slightly more complex. For example, in this case, you would have an e to the lambda 1x, an x e to the lambda 1x, x squared e to the lambda 1x, corresponding to the three repeating roots. Excuse me. And then you would have, for example, the root corresponding to lambda 3, which repeats twice. You would have e to the lambda 3x and x e to the lambda 3x. And for the rest of them, you will only have e to the lambda x's. Okay. So you'd have to form these combinations in the case of repeating roots by appealing to your knowledge of second order differential equations. Remember the rules that we wrote down for the particular solutions, right? So the same thing holds here. If you have one root repeating, multiply. So if you have, for example, one of these roots repeating 2 times, the solutions are e to the lambda x and x e to the lambda x. If you have the same root repeating 3 times, which can happen because we are dealing with higher order differential equations, then the roots are e to the lambda x, x e to the lambda x, and x squared e to the lambda x corresponding to that lambda. Okay. For those lambdas whose roots do not repeat, you only have one factor of e to the lambda x. And then you combine all these guys to form the linearly independent solution. So we will look at this and other examples of such cases. And we will also look at a practical example as to where these higher order differential equations can come into play in engineering problems in the next lecture. Today, I will stop at this and then we will continue this discussion on Tuesday.